Okay, so here's where we left off. We've got a set of curves here, and we have similarly some curves and some surfaces, and we're going to look at a couple different ways to build on what we just did. And just because I know that these are probably hard to see I'm going to change my layer color in this case to something that's a little easier to see, so I guess I'll just go with blue so that you can see it a little bit better. Okay, now there is an earlier sample. There was a kind of an earlier demo video that walks you through how to model those beam sweeps and orient the cross-section curve using Grasshopper. That hopefully gives you some sense for how to use the software. I haven't gone through and kind of introduced this in a more slow way. We could do that, and I think this example here is probably a little bit more lightweight than the last one. So what I'm going to do is just kind of walk you through how you can interface Grasshopper with these curves to go ahead and model up, first of all, a wireframe that's more polygonal with straight edges in between that we can't derive from the surface that we drew manually before. So that's the one that we drew manually over here. Okay, so we'll do that. And also how we can break these surfaces down into planar pieces. Okay, so I'm going to open up Grasshopper. And I'll share my screen a little bit, kind of half and half. And the first thing is there's a set of parameters over here, which what these do is kind of hold geometry either from GH itself or from Rhino. And because we're not developing anything from scratch yet, I'm just going to walk you through how we can get these curves into GH first. So let's go over to our parameter tab here and look for the curve parameter. Okay, and that's going to look like that. And the other thing is we can change the display. So if you're not seeing the icons, you can turn the icons on or off using the display. Another thing to do sometimes that people like is the full names so that you can see what it's called. And I guess I'll use that, for this example. It's a little bit easier, I guess, for you guys to follow along. What I'm going to do is right-click on this and go down here to Set Multiple Curves. And I'm going to just click these to develop a good habit. You don't necessarily have to do this, but sometimes it's important to click these in order, so I'm going to suggest that you get into the habit of it. And then you can hit enter when you're done clicking those, and now those curves will be set and understood to be part of the Grasshopper environment here. And if we hide these curves, you'll see that they're rendered out in red here. That just means that it's the Grasshopper default, but they're not selectable in Rhino. That just they're only existing right now as data in Grasshopper. And the reason for that is that when you're dealing with more complex files, to have a ghosted preview basically of what the geometry actually is speeds up your computer drastically. And only later when you're ready to make it real, you can bake it into Rhino again. And I'll show you that. What we want to do is, remember going back to what we did over here, we want to use the same process just in Grasshopper, so we're going to divide those curves into points. And hopefully you're getting the sense that the stuff that we covered earlier will match some of the things that we're going to do now using Grasshopper. So while we were trying to introduce you to ways of modeling in Rhino, we were also introducing you to conceptual ideas or concepts on how to use Grasshopper as well. Which is why a method is more important sometimes than a series of buttons. So learning it sometimes is better to learn the method. And then you can create your own. I'm going to go to the Curve tab up top, and I'm going to select Divide Curve. Okay, and I'm going to plug that in there. Okay, so I'm going to plug that in, and all of those curves now will be divided because I have a set of data, 13 curves, and all of them will be divided using this thing here along a count that I set. And I think the count we used before was 25, so I'm going to go over to Parameters, and I'm going to use what's called a number slider here. I'm going to hit Edit, so right-click, Edit. You can turn that to number, so hitting the N button here, and then double-click into the max field and change that to something like 25, and then hit the green button. Okay, and you can plug that into the count. Now, of course, when it's 0, you'll see no points. When it's higher, you'll see more points. Okay, so we've just made our divisions. Let me get a nice zoom on that somehow here. Okay, I guess that's all right. And these divisions, I think, are the same as what we saw before, right? And now if we take a look at what's coming out of here, the data set that's coming out is the points, and you can see how it's organized. So on the left, that's representing each one of the curves separately, and on the right, n equals 25 equals how many points you have on each one of those curves. And it's dividing all this data for you so that it's basically segmenting or partitioning the point data to be specific to each curve so it knows where they are. That's helpful in the next step, which is to connect the dots. So one thing we can do now is to go over to Curve, Spline, Polyline, and just click in on the vertices. And what I want you to do now is to go over to the curve originally here and just right click on that and turn off the preview. And let's take a look at what that just did. So by default, because of the way the data was set up, it started drawing our polyline through each set of points individually. So we have a set of individual curves that we didn't want to draw, but I wanted to show you this as a way to talk about how Grasshopper will sometimes set up the data for you. The other thing it didn't do is make the connection, and here it's going to ask you whether or not you want to close the polyline. You can right click on that, set the boolean to true, and it'll close it off. Now, if we wanted to draw the lines in the other direction, the only thing we need to do in this case is just to kind of flip the matrix so that the points are associated with one another across instead of along the same line that they were drawn from. So instead of going from 1 through 25 in this direction, we'll go through 1 through however many in that direction. And because these are all ordered in the same way, I'll be able to connect the dots evenly. So go over to Set, and into Tree, you'll find the flip matrix component here. Flip that matrix that comes out of the point output, and then replace that. Oh, we got a problem. Okay, and you might recall one of the things that we did earlier was that we flipped one of the curves around to get the loft to work, and that's what's happening here. One of the curves that we input in is flipped, and it's probably this one here in the center. So show those curves again. Go ahead and click on that one and flip it. So type in flip and flip it back. So now we're seeing a much more desired result. Okay, and so it comes down to inputting the effect of what's happening in Grasshopper will also take with it some of the stuff that is true in the Rhino work. And because that curve had a direction to it that was opposite the others, we had that kind of twisting issue. So when you encounter issues like that, pay attention to the kind of stuff you're bringing in. It may not be that you're too far away from getting it right, so try not let that throw you. The other thing we want to do is just make sure that this is also set to false again, or not. Oh, sorry, I just made it true again. So you might have been seeing this just a second ago, and that's because we're closing out the polyline to go from start to end, and that's not what we want in this case. So we can set that boolean back to false, and that gets rid of that line. Okay. And so here, what we've got really quickly, instead of drawing it manually again, is just that set of straight polylines across that connects the dots, which could be the beginning of the framework that you'll use to draw out the panels, or maybe even use this as a drawing to line weight these a little bit heavier than the panels in between so that you can show that there's some kind of framing there. I think you get the idea. But basically what we've done is, in this case, we've just drawn a custom wireframe from the sections themselves that the surface itself did not provide. And if we wanted to put this into Rhino, what I would do in this case then is, once again, I would go back and hide these. Okay. And now we need the curves going in the other direction, so you can copy and paste this polyline and just bring it through from the original data set like that. And now we've got all of our wireframe lines drawn. If you don't want to see the points, you can turn those off. Just kind of right-click, disable the preview, and there's your polygonal approximated wireframe. And in this case, on these, we want to make that boolean true to close that off. Okay, so we're all complete here. And then what you can do is you can right-click on these components and bake these on whatever layer you like. I'll bake them on layer 5. Right-click, bake, layer, and then now they're selectable in Rhino. So we've made them actual curves instead of just previewed. So if I zoom in on that again, you'll see I've got a set of polylines drawn really quickly. So what we've done is we've automated what normally would have been a long manual process of creating these. And now what you can do is, again, just to show you, we can start building in our panels and begin skinning the system. And we can also use Grasshopper for this, but just to demonstrate the idea. And there you go. So there's one example. Let's move into the next example, which is going to be to break these surfaces down into planar components, truly planar components. Okay, so, and to do that, I'm going to move this again, maybe a little bit over here so I can, free up my screen a little. Okay, let's get started on that. Okay, so just like we brought in the curves here, I'm going to bring in the surfaces instead. Okay, so I'm going to go back over to the parameter tab up top here and look for the surface component here. Okay, so I'm going to grab that. Right click on that and you can just set one of these surfaces in. I'm going to select that one. And then I'm going to hide the one that I just put in there. Okay, and zoom in on that surface. And now you can see that where the seam was, we're seeing a line. It's revealing where the start and end of that surface actually is, which Rhino doesn't always do. What we want to do now, I'm going to introduce you to a way to subdivide a surface. Okay, which is kind of like drawing custom isocurves along that surface, but then splitting the surface using those isocurves to do it. So it's going to create a set of new surfaces from this one here that are separate from one another. So I'm going to go over to, first of all, I'm going to go to the Surface tab up top here and go to Utilities and ISO Trim, it's called. Right? And you can plug your surface in here, and now what we're going to need to do is give it a domain, and this is going to be your UNV value, basically a grid, the number of lines you want to draw across the surface, the number of seams. Okay, so we can go to Maths, Domain, and go all the way to the bottom to divide domain squared. And you can go ahead and click the surface into the domain here, and then the output of that into the domain that we had in isotrim. And then please go ahead and disable the preview for our original surface. Otherwise, that overlapping preview can get really distracting. Okay. Now, if we hover over the output here, it looks like we have 100 base surfaces. That's, sorry, surfaces that are trimmed, untrimmed surfaces from the base. And that's because the UNV count is 10 and 10. So it's drawing 10 in the long direction and 10 in the short direction. That's obviously not the breakdown that we think is ideal here. So we can go grab one of these panels from, and you can use sliders for this as well if you like. Actually, I'll just use the same slider we had before. And I'll just decrease, I'll grab two of them. I'll plug this into the U count. And that's the one I want to decrease to something like maybe just 3. And go ahead with the increase that V count using that slider as well. Okay, so now we've got more or less square panels that are being drawn across. And we can make them more rectilinear as we like. Oops. You don't ever want to get that down to 0, of course, because that'll just throw an error. So let's work with longer panels for now. So I'm just going to go with 2 and 25 just to kind of show how we can take these curves and planarize them. But if you're happy with these as being curved panels, let's say they're being formed from metal and stamped or something, this is a pretty good way to go. And now you've got your surfaces ready to be baked out. So if you want to see what that looks like, we can bake these. And you can see now that we've got a set of separate surfaces that I could use however. Okay. All right. So let's go back to that the four corner point logic. And this goes all the way back to how we looked at modeling the boats potentially in terms of the long strips, the ship lapping. Same logic, and also something similar that we did earlier in part 1 over here, when we started talking about how you can model custom panels within 4 corner points. So I'm going to go back over here. Okay, what we need to do is extract that information, which we don't have yet. So I'm going to go to Surface, Analysis, and Deconstruct BREP. Okay, so this is it's kind of like exploding, and I'm going to disable the preview of the original. It's kind of like exploding those surfaces into what makes them. So the face is the surface itself. You got all 4 corner edges and then all 4 corner vertices. And the vertices are what we want to deal with. But what I need to do is extract each one of these 4 into separate pieces, or into separate data points, so that I can draw a new surface from it. So I'm going to go over to Sets up at the top here, go to List, List Item, and input that, and then disable the preview. And now I'm going to zoom in on this list item and hit the plus button a few times until I have I, 1, 2, and 3. This is basically a 0 index, and then 1, 2, and 3. It's representing all 4 of the points of each one of the surfaces that we just deconstructed. Okay, and we can use these points now to redraw a surface that's flat but kind of twisted. So it's not planar, but they're as flat as we can get them, at least from these points. So I'm going to go to Surface, Freeform, 4 point, and just to connect across like this. Okay. So let's zoom in a little bit and see what that looks like. You can see we've got some considerable twisting in this area. And that, is going to be up to whether or not you can achieve that. If you can't, you did notice, let's disconnect this one. You did notice that if we only connect 3 points into this component, that you could build a triangle. And if we wanted to build the other triangle, we can figure out what points, we can just kind of trial and error this to see which ones. That's the wrong one. One thing I like to do in this case is sometimes I like to go over and go to Display, and I like when it shows us what the point list actually is. So if I zoom in a little bit, and actually I'll go to Sets first. I'm going to grab one of these, just one of these panels. So that's going to give me just one of these panels here. Then I'm going to copy and paste this deconstruction here, and this is something I like to do just as an analysis tool, right? Because then I can figure out what the order is a little bit more clearly. And I'm just going to increase the size of this point list so I can see them. Yeah, so now I know that it's a little bit big. Yeah. So now I know that this is the order. It's counterclockwise. So I know that point 0 is going to be in that bottom right corner on every single one of these panels. So that's going to be really helpful when it comes to connecting the dots. And the dots I'm trying to connect now, let me turn that off. The dots I'm trying to connect is 0, 3, and 2, whereas before we connected 0, 1, and 2. All right? And this just saves me some time. So I can connect 0 to 2, and then to 3. Okay, so I've drawn the other set of triangles within that, in between those 4 corner points. And now I can turn that off because it served its purpose. And what I have now is a kind of a triangulated set of panels that could have a fold in the center, or you can fold across in this direction. It's really up to you. So you can have a big diamond-shaped panel that's folded that way, or you can have a panel that's more rectilinear but folded along its long edge. And that's going to relieve some of that twisting that's going on in here. So now they're all flat again. Again, there's a very particular aesthetic, and maybe that's not what you're going for. So let's walk through how we might planarize these panels instead. Okay, so I'm going to use that as a little tester. I'm going to turn off the preview here for these, and I'm going to go from this point where we were before. Okay, so I'm just going to go back to that surface tab, grab this same command that we used before, the 4 points, and I'm just going to build a new one, except this time I'm going to build all 4 instead of the triangles, like that. turn off those previews because don't need them anymore. And then the next step, what we're going to do now is, what we need to do is find kind of an average perpendicular direction. And what we're going to want is the perpendicular direction from the center of this panel in space. And we're going to use that perpendicular direction to set a plane that will project all the points onto. And that will end up being the plane at which our new panel is, from which our new panel is oriented in space. And that's going to minimize the amount of gap in between the panels as best we can. And I'll show you that in just a second. So let's keep moving here. So what we're going to do is we're going to go to Surface, grab this little area component there, and try to find a center point. But this center point, because these surfaces have volume, because they're twisted in space, is not going to reside directly on the surface itself, and it's not going to give us the information that we need. So we're going to go over to Analysis again, grab two components, the surface closest point, and this one here, Evaluate Surface. Okay. If you're having trouble finding the icons, you can double-click in here to search for the keyword, and you can type in something like Evaluate, and then Evaluate Surface comes up, click it, and it pops the component onto the screen. It might be a quicker way to follow along if you're comfortable with that. The surface closest point is going to grab the point that we just found from our area here, and it's going to force it to reside along that surface. So it's going to kind of pull it and draw it to it. And you can see as an output here, I've got something important, which is the UV coordinate of that point. And we're going to need that in here to find our normal direction. Okay, so we can grab the surfaces like this and then use that UV point as an output. Now, what happened now is what I'm seeing is a lot of overlapping frames. Go to Display. If you're seeing this, go to Display, Preview Plane Size, and make this something much smaller, like 0.2. Hit Enter, and now we've calmed down our preview. And you can see that I've got a plane that's residing along all those surfaces in plane, well, kind of along the perpendicular direction of that plane. And a plane, by definition, is planar. All right, I'm going to turn off that preview because the plane sometimes gets a little bit distracting, and I'm going to use this normal direction, or the frame actually, in order to, as the projection. Actually, maybe I will turn that on. Yeah, that's cool. One thing I did want to show you too is what the normals actually are and what that looks like. So you can grab in the Display tab, you can grab this vector display component, and you can use our point as an anchor and our normal as a vector. And what we'll be seeing is a set of arrows that come off the surface in those perpendicular directions. And what we got here is a flipped surface, so the upper, let's say the normal is inward facing. That's not such a big problem. We can either reverse that or we can just flip the surface in Rhino. But in this case, it doesn't really matter. But I did want to just show you that to give you an idea for what I was talking about when I said normal direction. And also, this frame is oriented now in that direction, perpendicular to it, which is very helpful. So the next step that we're going to do is project all those four corner points, these guys here, from over here. And what I'll do is I'll just take this stuff and I'll just kind of move it down a little bit so that I can more easily drag that across. You know, it's just kind of keeping things organized. And I'm going to go over to, I think it's in Transform here, Affine and Project onto a plane. Okay. The geometry that I'm projecting are the vertices. The plane that I'm projecting that onto is the frame that came out of our last process here. Okay, and it's not going to look like a whole lot changed, but if you zoom in, what we should be seeing is a new set of points that deviate off of, they deviate a bit off of the original surface, and that's because now they're projected along that plane right there. We can use those points because they're organized into fours to draw a new surface that's planar. So here's where we can turn that off. We can now go over to Sets, List Item like we did before. Geometry goes into the list input, zoom in, hit the plus button a few times, extract all 4 of those points, and then rebuild the surface through that. So surface, 4-point surface, as such. And then what we want to do is go back and turn off the preview for the original surfaces that we modeled. And what you're going to see are the gaps in between the panels. And that's not such a bad thing. We know now that these panels are truly planar, which means they can be built from glass. But the trade-off is that you have to have something that takes up the gap in between here. So you need a frame, a mullion, something that would hold these panels in place so that this gap wouldn't allow leaking and so on. But this is a pretty common architectural problem when it comes to curved surfaces. If you increase, of course, the density, we'll probably have less of that happening. And I'm going to increase the values that are possible out of this slider, kind of like what we did before. And you can see that I have even less deviation now because I have to go a shorter distance in between the points, so I have less gaps. So in this case, the more panels you have, the more accurate. Let's see, the closer the approximation of the curvature that you'll get, but you're always going to still have some kind of gapping issue when it comes to approximating curvature, especially something that's twisted and complex like this one. And that's just something that you'll have to deal with. Let me show you an example. I'll go back to 25 here and 3. Let's look at an example. Foster and Partners Smithsonian canopy is probably a pretty good example of this. You can see from some of these images here that you're getting this kind of undulating canopy structure that floats over the courtyard. It's got a diagrid frame, and within each one of those framing pockets, if you will, the space between the frames, there's a glass panel. And you can kind of see how the light filters through. The top of that looks like this. So those glass panels are held within a frame, and these are all planar pieces. And you can see the kind of how the gaps in this case were just formed into boxes, and there's a waterproofing detail that keeps the rain out while still allowing for the construction feasibility of this kind of complex curvature. And you can see the top view of it. You can see how that undulates into these kind of doubly curved forms. And here's a construction photo to show that relationship going on in action. Let's see if we can, well, looks like it's a small image, but you get the idea. And here's another one. So the planar panels being placed into the frame. So long as the frame is deep enough and is detailed with the right offsets and structural members, you can get the planar piece to fit within that, while still, while not really compromising much of the overall architectural idea, right? You still get this kind of undulation, but you're doing it within the, within the confines or within the parameters of the material. Okay, so that wraps up this introduction to planar panels on curved surfaces. There's, of course, much more that we could talk about, and I know that your projects will get more specific, but hopefully this provides a pretty good foundation for you to keep moving forward, and a little bit of a lightweight introduction into how we might use Grasshopper to assist with the modeling of these skin systems.